We start with exercises based on all the previous theorems that we've done all the way to cyclic quadrilaterals. The first exercise, we are given A, B, C, and D, F as tangents to the circle. And we have BOE, a diameter, and then we've been given GBE to be 50 degrees as labeled, and then also given that GE is parallel to BH as labeled in the diagram. Then we're asked to find angles X, Y, Z, P, and Q. And we have to offer reasons. Firstly, I said angle Q is equal to 50 degrees. Angle in the alternate segment is equal to the angle between the tangent and the chord. And also the angle between the radius, which is a diameter in this case, and the tangent is always equal to 90 degrees. Therefore, we're able to get P. And then we go on to get the value of P, which is 40 degrees. And then thereafter, we find the value for X. Again, we're using the fact that Y and Z are equal to 90 degrees. And therefore, X definitely will be equal to Y. But in this case, what I've chosen to use is that angle EBC is equal to P because of those two parallel lines. And therefore, P and angle EBC are alternate angles. They're equal. Therefore, because P is 40 degrees, that means even that angle is 40. Therefore, X is equal to 50 degrees. The angle between the radius and a tangent equal to 90 degrees, or you can simply use the tan chord theorem that Y is equal to X. And if Y is equal to X, then we're able to get Y, which is 50 degrees, tan chord theorem. And then lastly, Z, it's definitely going to be 40 degrees, 90 degrees for that angle between the diameter and a tangent. There are many other ways that you could use to get those angles, because you could even decide to calculate the angle H, which is an angle subtended by a diameter, or should we say angle in the alternate segment, to get 90 there. And then because you already have Y equal to 50, then it's easier then to be able to get X to also be equal to 50 degrees, and then you'll be able to get Z to be equal to 40, angle between a radius and a tangent. We'll move on to number 2. I've solved this one partially, and I expect you to finish it off. Note that we've been given that the radius for the small triangle with center O is R, and the one for the bigger circle is 2R. So I'll just indicate here which lines are equal based on what we're given. So OB and OA and OE, they're equal. Okay, and MA, MD, and MC, they are also equal. So MA, MD, and MC, they are all equal to R, and the other to OB, OE and OA are equal to R. But then the first question, we have to prove that MD is parallel to OE. So for parallel lines, we have to find the angles that fit FUN. Any, we can get corresponding angles or cointerior angles or alternate angles. And in our case, we decided to use that D1 plus D2 is equal to 90 degrees. The angle between the radius and the tangent is always equal to 90 degrees because the radius and the tangent are perpendicular. Also, OE is perpendicular to the tangent, okay, DP. Therefore, all the angles E1 plus E2 equal to 90 degrees and also E3 plus E4 equal to 90 degrees. Okay, so because of that tangent, that means D1 plus D2 plus E3 and E4, we're getting 180 degrees. And therefore, it meets the rule for interior angles. Therefore, we can be able to say MD is parallel to OE. Just to move on, just quickly checking all the angles that might be equal here, not necessarily helping us to prove that BP is equal to 2R, but I'm noticing that D1 is equal to angle C, angle in the alternate segment. Also E1 is equal to angle A1, angle in the alternate segment. Also E4 is equal to angle OBE. And then base angles. So that means A1 will also be equal to E3. Base angles of an isosceles triangle because OE and OA are equal. Also, here we have E2 equal to angle OBE, base angles of an isosceles triangle because OB is equal to OE, they're equal to R. Okay, and also we have base angles on the bigger circle. D2 is equal to A3 because MA is equal to MD, and we also have C equal to D3, base angles of an isosceles as well. So we find that C and D3 and D1, they are all equal. Okay, and coming back to this smaller circle, E1 equal to A1 and E3, they are all equal. So we're able to get a whole lot of angles that are equal. All right, and E4 definitely equal to angle OEB, angle in the alternate segment. So there are many angles that you can find that are equal and be able to use if needs be to prove that BP is equal to 2R, and because we've got diameter that has been extended all the way to P, and you've got a tangent to the circle. So that angle, definitely, angle P is equal to an angle there. There's a theorem that links the two. So we might be able also to realize that AO plus OB, that's equal to 2R. That's 2R. And note that this is equal to MA, equal to MD, equal to MC, based on what has been given, because the radius for the big circle is 2R, but the radius for the small circle is R. So therefore the diameter of the small circle is equal to the radius of the big circle. Now you are asked to prove that also BP, the diameter of the small circle, is equal to the line that has been extended all the way to P. Please prove this, and also you've been asked to find PD, and it must be in terms of R. Please attempt this and see which theorems that you can be able to use to assist. Then we move on to similar triangles. Note by definition, two triangles are said to be similar if those two hold. And guess what? If either of the two conditions holds, then the other holds automatically. So if you've proven that corresponding angles are equal, that means the two triangles are equiangular, then it means the corresponding sides are in the same proportion. They are not equal, but are in the same proportion. Okay. Then we've got theorems and corollaries based on the definition. You need to recall that if you've got a line that is parallel to a side of a triangle, and this line cuts the other two sides so as to divide them in the same proportion. So this line that is parallel to the third side cuts the other two sides in proportion. This number 2 is the converse of number 1. And then we go to number 3. You've got now two triangles that have got angles, corresponding angles that are equal. Then their corresponding sides are proportional. As it was said previously, that if either one holds, then the other one holds automatically. And then number 4 is the converse. If you've got corresponding sides of two triangles proportional, then it holds that the corresponding angles are equal. Then the corollary based on similarity is given by number 5. We've got now two triangles here, triangle ABC and triangle DEF. And then if A is equal to angle angle A is equal to angle D, and also you've got the proportion C divided by F equal to B divided by E, then you can be able to say those triangles ABC and DEF are similar. Let's do some examples. The first one, we have here DE, a line parallel to the third side of the triangle, cutting the other two sides in proportion. So therefore, You may say AD divided by DB is equal to AE divided by EC, or you may say AB divided by AD equal to AC divided by AE, and you'll be able to solve for the problem. So I chose to use AD over DB equal to AE divided by EC so that I can be able to solve for X. And note that in my calculations, I got X equal to -4. And because X represents the length of a side, so it cannot be negative. Hence, the only answer we have here is X equal to 3. Please check my calculations and see if you'll get the same. And then number 2, it has not been solved. AB has been given to be 2 and DC is given to be 3. And we've been given that A is 60 degrees. So if A is 60, then we are able to get that angle to be 30 degrees. And if it's 30 for triangle ABC, then it means we're able to get angle DBA. So that angle is 60 degrees. Angles of a triangle are supplementary. Because angle ABC has been given to be 90 degrees, so that means it goes without saying that 30 degrees will be equal to angle ABD. Based on what we are asked to determine, we're asked to find the side AD and the side BC. You may choose any of the two triangles. You've got here triangle ABD and you've got triangle CBD, or you may choose triangle ABC and triangle CDB or triangle ABD. So choose the one that is most suitable, that will be able to give the side AD and the side BC. Prove similarity first of those two triangles that you choose to use. Note that you have equiangular situation here, because even if you've chosen CDB and ABC, B is 90 and you've got here CDB is 90, and you've got 60 degrees, which is angle A, which is equal to angle DBC, and we've got 30 degrees for angle ABD, which is equal to angle C. So equiangular between a triangle CDB and triangle ABC. Or even when you've chosen to use triangle ABD and CDB, also you get a similar situation where you get similar triangles. So choose the ones that will work for you in order for you to be able to have that the proportion of the sides that will be able to help to calculate AD and BC. Okay. Based on what we are asked to prove, that PT squared is equal to PA multiplied by PD, and PT is a tangent, then we are able to use the triangles that have got the common side, which is PT. Therefore, we're able to note that we can use the big triangle and the small triangle, which is TAP, and the big triangle PTB, and be able to prove similarity, so that we can be able to use proportion based on similarity. I'm noticing that A1 is equal to T3, T1 is equal to B, angle between a tangent and a chord is equal to the angle in the alternate segment. We can start there and be able then to prove that those are equal, similar, not equal, similar. Also, one thing that we note is angle B, angle P, and T1 and T2. They are angles of a triangle equal to 180 degrees. Also, in the smaller triangle, P, T1, and A2 are equal to 180 degrees. Angles of a triangle are supplementary. Then, because PB is equal to T1, and we had said A1 is equal to T3, then we are able to say that T1 plus T2 equal to A2. T1 plus T2 in the big triangle equal to A2. So we've got three angles that are equal. Therefore, we can be able to say that we've got equiangular situation for these similar triangles. Okay, and then thereafter, we can be able to use proportion. BP divided by TP. BP divided by TP is equal to BT divided by PA equal to PT divided by TA. And then we take the two. That will give us that expression. Please write it down and see whether we got everything correct. So you start by angle B is equal to T1, tan chord theorem. Angle T3 is equal to angle A1. And PT1 and A2, 180 degrees, B and P and T1 and T2 equal to 180 degrees, angles of a triangle, and therefore we're able to say T1 plus T2, because P is common. You have to remember that P is common in both triangles, the big triangle and the small triangle. Then you are able to say A2 is equal to T1 plus T2. Therefore, those two triangles are similar, and then use similarity, noting the angles that we had said are equal. So even when we're naming our sides, we have to consider that. So that means BP divided by TP in the smaller triangle is equal to BT divided by PA equal to PT divided by TA. So PT, we used it for the smaller triangle, and now lastly we're using it for the bigger triangle, and then we're able to prove what we have been given. Write it down and be able to see that we did everything correctly. We start out this exercise by noting that CA is equal to CB. CA is equal to CB. So I'll just indicate this. CA is equal to CB. So we've got base angles of that triangle ABC. So that means A2 is equal to B2. Also, B2 is equal to angle ADC. They're subtended by the same chord AC. Also, A2 is equal to angle CDB, subtended by the same chord BC. And also, DB subtends A3 and C3. Also, you've got the angle between the tangent and the chord, which is C1, equal to the angle in the alternate segment, which is angle ADC. Also, angle DBF is equal to the angle in the alternate segment. That means it should be angle A2. So work it out and be able to prove triangle CFB is similar to triangle DCA, and then thereafter prove that CB squared is equal to FB times DA, noting that CB is the common side. Work it out and try. Then next exercise, we're still using similar triangles again. AB is the tangent to the smaller circle, and CB is a common chord. So choose the triangles that you're going to work with so that they have BC, DC, AC, and EC. One thing that I can just quickly point out is that BC is a chord, so that means A2 and angle BDC are equal. And I believe also that BA is a chord in the bigger circle, and therefore C2 and angle ADB are equal. Also in the bigger circle, CD is a chord, so that means A1 and B1 are equal. And also B2 and A1 are equal, subtended by the same chord, which is AB. So can you please work it out and choose well the triangles that you're going to work with, and be able also to prove B that angle ADC, that whole angle there, is equal to angle BAC plus ACD. That means BAC, which is A2 plus C1, are equal to that angle D. And also AB squared, that means now you're choosing different triangles. These triangles have got AB in common, and then prove similarity. Please work it out and attempt and see how far you go.